One problem I have when I printed these things out before I came over here was that I failed to include the question number. So I've just done a little, because sometimes you forget things. I scrambled, but I think I've got them organized, and I'll try to keep up as best I can with what's available to us. Hopefully, because I can do this, that will make our lives more simple. Let me make sure. Has anybody got Sakai open? Can check announcements real quick. Just make sure that link is live. That would be great for me. And if it's great for me, it's great for me. Thanks, Katie. Cool. All right. I got scratch paper. I got, look at this. Look at this assortment of pens. I've given up on that multicolored singular pen. I still don't have an orange pen or a yellow pen, but I have full assortment. Like, I'm pretty excited about that. So I'll be able to color in all sorts of stuff, provided we get started on questions. So anybody needs a Z table? They're up here. I think we're all equipped. Hey, it's 4:30. Let's do something, shall we? Yeah, let's do it. All right. I think there's 49 questions broken up into 11 multiple choice, followed by 12 true false, followed by a couple more multiple choice, and then 5 questions to work through. I think 2 hours is absolutely a good amount of time. Let's get started. What happens to the standard error of the mean if the sample size is increased? This is going to be one of the biggest questions that we get answered out of this particular module and going forward. I'm going to spend, I know it's only one question and it's only 2 choices, so you can probably get the question right. A or B? What do you think? A or B? Standard error, what happens to standard error if the sample size goes up? What do you think?
Increases.
Nope, the other way. Here's the way it goes. So, standard error of the mean comes in one of 2 forms, either as sigma sub x bar or s sub x bar. And they both do the same thing. In fact, when we see the other 2 forms of standard error that we're going to be using, the ones that we use for proportion, because both of these are for the mean, and we know they're for the mean because they contain standard deviation. The other 2 that we use will look like this. In all cases of the standard error that we use, the sample size is the denominator. Sure, it may be square root of sample size, and that just makes a number greater than 1 get smaller. But in all cases, the denominator of the standard error gets an n. So we can say for any standard error, we have something, either a standard deviation or some PQ, we have something over the square root of the sample size. Now what we said for question 1 is what happens to the standard error if the sample size is increased. This whole thing is the standard error. If n gets bigger, what happens to that fraction? If you have a big denominator, what happens to the fraction? Bigger?
It's going to decrease.
Yeah, it's going to decrease. It's going to get smaller. And we can actually take that one step further, because when we calculate a standard score or a z-score, it's always going to have standard error on the bottom over sampling error. So if n gets bigger, the standard error gets smaller. If the standard error gets smaller, z gets bigger. So So if we have a sample size n gets big, standard error gets small. The standard error gets small, our test statistic gets big. Those three things are going to have that relationship. We're going to use that from now to the end of the semester. The bigger the sample size, the smaller the standard error, however we calculate it. The smaller the standard error, the bigger the test statistic, or the bigger the standard score, which we'll soon be calling test statistic. But bigger that makes smaller that makes bigger that. The answer to question 1 is A, 1 down, 48 to go. 2. What happens to the distribution of sample means if the sample size is increased? Why do we need the central limit theorem? The distribution of sample means. What happens to those that distribution of sample means as sample size gets bigger, Tom? Becomes more normal. I mean, of those three, that's the only one we can think of that we've even talked about in here. But for whatever population we have, and it doesn't matter, we can have a small sample size or we can have a big sample size. We've already seen what that does to the value of the standard error. But a small sample size means our sampling distribution might represent the population. It might look like the population. In fact, with a small sample size like n equals 1, it will be the population. Now with slightly larger sample sizes, it won't necessarily look exactly like the population, but we know with a large enough sample size, we're going to end up operating under the normal distribution. That's why we love the standard error, because it lets us use that table. Time check. 2 is B, or normal. 2 down, 47 to go, 3. When using the distributions of sample means to demonstrate or to estimate the population mean, what's the benefit of using larger sample size? So the shape of the distribution becomes narrower since dispersion is less and estimates of the mean are less precise. Looks like we've got a double-barreled answer. The shape of the distribution becomes narrower since dispersion is less and estimates are more precise, or the shape of the distribution becomes narrow since dispersion is more and the estimates of the mean are more precise. We've just got 2 different answers juxtaposed there. Which of those 3 contains all truth, no filler? Well, let's eliminate one. Let's eliminate one of those 3 things on the basis of a bigger sample. Should a bigger sample intuitively provide us more precise or less precise estimate? Bigger sample, more precise, Meg?
More precise.
More precise. So which one of those can I eliminate?
A.
I'm going to eliminate A. So the shape of the distribution becomes narrow since dispersion is less, or dispersion is more. That's the only thing that differs between those 2. In both cases, we have more precise. And this was a bit of a question. This was one of the true-false questions from your midterm, either question 2 or question 7. I don't know. Maybe not. Could be. It'd be cool if I was right, but it doesn't matter. If you have lots of dispersion, the distribution is spread out. If you have a little dispersion, your distribution is narrow, which means most of your estimates are similar. You have less dispersion if most things are the same. So round that up, lasso it into an answer. Distribution becomes narrower since dispersion is less and estimates are more precise. 3 is B. 3 down, 46 to go. Number 4. Process Trucking Company claims that the mean weight of its delivery trucks when they are fully loaded is 6,000 pounds and the standard deviation is $1.50. Assume the population follows the normal distribution. 40 trucks are randomly selected and weighed. Within what limits will 95% of the sample needs occur? There's 4 pieces of information that we can definitely identify from this problem. Now, this is where we really start to need to get in the habit of, sure, we know which things are means, we know which things are standard deviations. I can tell you that when it says standard deviation is 150, that means standard deviation equals 150. Problem is, we got 2 different versions of standard deviation. We have sigma and we have S. We also have a mean here because it says the mean weight, blah, 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 is 6,000. The mean weight is 6,000, just the same way that the standard deviation is 150. So that 6,000 is going to be a mean. That 150 is going to be a standard deviation. Okay.
Just want to double check. Read, circle A. We're going with it. You know that?
Yes, we are. I need that. Loose today. Good. 3B. Anyway, we have a mean and a standard deviation. Are those population means or sample means? To put it another way, are they expected or are they observed? If they're observed, I'm going to ask you how many observations were made to arrive at said observation. Or are they expected? If it's expected, I want you to tell me who told you that or why you expect it. Colin. It would be expected. Why do we expect it? Yeah. Yeah, they tell us what it is, so we expect it to be that value. So these are expected values, mu and sigma. 2 down, 2 to go. We assume that the population follows a normal distribution. That's kind of cool, but we got 40 trucks are randomly selected. 40, I need a symbol for 40.
Lowercase n.
Yeah, little n. So now we end up in a situation. If we were looking at a single truck, which we are not, because again, we are looking at 40 trucks. If we were looking at a single truck, and we wanted 95% of stuff, I would take 150, subtract it once, subtract it twice, and say 5,700. Subtract it once, subtract it twice, get to 6,300. If we only had 1 truck, that's what I would go with. But how many trucks do we have? 40 trucks. Some of those trucks might be a little bit over 6,000. Some of those trucks might be over 6,000. But we expect on average that they're 6,000. So we wouldn't expect 40 trucks to have a mean as low as this, or 40 trucks to have a mean as high as this. 1 truck, sure, 1 truck could be down here or up there, but not 40. So in order to take that into account, we have to find another piece of paper. How about this one? Mu is 6,000. Sigma is 150. N is 40. And we have to calculate the standard error. $150 over 40 is 2 times the square root of 10, which is 150 divided by 2 times the square root of 2 times the... I'm going to keep doing prime factors and square roots until somebody can pound a computer or a calculator or ask Siri. Basically, I need to find the value of the standard error so that we can use the empirical rule. How'd the tour go? Good?
Great, thank you for asking. Yeah. Oh.
Sorry, I didn't have more time. But we got. 23.7 pounds, right? 23.7 pounds?
Yeah.
Yep. 23.7 pounds, like 24 pounds. I mean, in terms of big old trucks, 23.7 versus 24 pounds, I'm gonna call it 24. I'm gonna keep my life nice and simple. That's somewhere around 24 pounds. 6,000 plus 24 twice, minus 24 twice. I think somewhere between those two values, I will find 95% of stuff. And I hope there's an option in number 4, something like 59, 52 to 60, 48. John, we got something?
We got 59, 54, and 60, 46.
I'm comfortable with that if you are. Cool. I got a smile and a thumb. I'll take that. Yeah. 4. Call it a 5? Is this 5? Southern California? All right. In a certain section of Southern California, the distribution monthly rent for a 1-bedroom apartment has a mean of $2,200 and a standard deviation of $250. The distribution of the monthly rent does not follow the normal distribution. In fact, it is positively skewed, like the palm of your right hand, which means this is how much money. Very frequently, there are low-cost apartments, and more frequently, are there really nice places. There are many low-cost apartments, and there are few high-cost apartments. That's what we mean by positively skewed. What is the probability of selecting 50 1-bedroom apartments and finding the mean to be at least 1950? I'm going to tell you the answer is not, cannot be determined. I'm going to tell you what else. What do we got? 1, 0, and 0.1. It's a contact sport. Let me give you some exposure. Come on. So give me a couple pieces of information that we know we can identify from this problem. We know it's not a normal distribution, I got that. But there are a certain couple other things that we can figure out. What are the other things we can see? Jack?
Mu is 2200.
Mu is 2200. While the distribution might not be normal, we know that on average apartments, 1-bedroom apartments are 2200, which is a lot, but it's LA. So that's one piece. What else we got? Rachel?
Standard deviation is 250.
Standard deviation is 250. And Katie, how many apartments are we looking for?
50.
50. Those are the 3 pieces of information we got. Mu is 2200, sigma is 250. There's no sample size associated with those. That's just we know to be true. But we're going to look for a sample of 50 apartments. It doesn't matter if our population is normal because our sample size is sufficiently large. It's greater than 30. So we can imagine that if we take samples of sample size 50, if I take a sample of sample size 50, I'm probably going to get a value somewhere around 200, and that's, or 2200, because that's mu. Doesn't matter what the shape of the population is. If the mean of the population is 2200 and I take a big sample size, I'm probably going to get something near 2200. It might be a little bit less, it might be a little bit more. It might be a little bit less, it might be a little bit more. The question says, what's the probability if we select 50 of them, that it is greater, the mean of those things, so much, is greater than 1950. So if there were one more piece of information that we included here, one more piece of information that we might include into some part of our calculation, what piece of information would that be? 1950. But I need a symbol to associate with it. What symbol is in that row? Jack? You weren't done speaking after you said X, were you? There was something else you wanted to say, right? Yes, you did. X bar. Because I'm going to take a sample of 50. And from the sample of 50, it's possible that I get a sample mean of 1950. It's possible that I get more than 1950. It's possible that I get less than 1950. But our question says, if I take a sample of 50 apartments, what's the probability that they average at least 1950? So our goal is to fill in the distribution to the right, and then that's our answer. X bar is 1950. I gotta stop using green because it's a 0.5 and those are garbage to write with. All these are 0.5. Even the gels. Boo that. They are the worst. But we'll still be able to use the same process we've used before, which looks like this. Because our goal is to find the probability that X bar is greater than 1950. My raw score, 1950, I convert into a z-score using the formula. 5 words I use to describe the standard score. What are the 5 words I use to describe standard score? Hunna, 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 hunna. Hunna, hunna, hunna.
Sampling error over standard error.
Sampling error over standard error. Sampling error over standard error. And I hope that when it comes time for May 11th and you're taking your final exam and you're like, how do I calculate a test statistic, which is an M for Z score, you go, right? My goal is to get you to remember it. At what cost? I don't care. Sampling error over standard error, which means I need to calculate standard error. Formula for standard error, we're going to leave here knowing this. Formula for standard error, I don't have that, but what do I have? Nope. That's what, oh, sorry. But what do I have? Sigma. I do have sigma. Sigma S, you name it, sigma over square root of n. That's going to get me 250 over square root of 50. It's going to get me like 25 divided by 7, which is like 33, 35? 35? So I've got some 35.3. Really, it doesn't matter. 35, we're going to see shortly, is the biggest point. Because my sampling error is the difference between what I observe and what I expect. So what's the value of my sampling error? Easy to calculate. Mary Claire? Negative 250. Perhaps you see why now I don't care whether it's 30 or 35 or even 40 for the standard error. Because what's the value of my z-score now? 7?
Yeah, negative 7.
Negative 7 point. You know what? It doesn't really matter at this point. It really doesn't. Is a huge z-score. Huge. I know it's negative, but it is 1, 2, 3, 4, 5, 6, 7 and change. It's that many standard error units below the mean. There are a lot of apartments in LA, and they are expensive. The average price is $2,200. If you find 50 apartments, the average is probably going to be around $2,200. 1950 is a steal. The standard deviation of a single apartment is $250. If you found one apartment in LA at 1950, that would be cheaper than 60 some odd percent of other apartments in LA. 64%. One apartment. One would be cheaper than 64% of other apartments in LA. Now we're saying if we find 50 apartments, what's the probability that their average is greater than 1950? Almost assured. My z-score is -7. My table only goes up to 3.9. As soon as I get to 3.9, this area becomes 0.5. And that half is already 0.5. What's 0.5 plus 0.5? 1. Five is 1. This is just like the problems, I think, just like the problems, that 1 or 2 that we've done in class so far, 3 depending on which section you're in. But that's all we do. It's the same process of raw to z to area to probability, proportion, percent. Looking at the faces in this room, I think we all got that. Is that right? Like, I graded your exams. I see you every day. I think this crew has it. Let's get through this and not waste any more time. Thanks, guys. Number 6, an experiment involving selecting a random sample of 256 middle managers for a study. One item of interest is their annual income. The sample mean is computed to be 35,000 and change, and the sample standard deviation is about $2,000. What is the sample standard error of the mean? Oh, sample standard error of the mean? Sample standard error of the mean. How do you calculate that? You'll know before you leave today. Formula for standard error, Jack?
Standard deviation divided by the square root of population size.
Sample size.
Same thing.
Yep. S over square root of n. Okay, we want the sample standard error. That's all this is, sample standard error. What's my value for S? Gotcha.
256.
Nope. That is my sample size. That is my N. Because I'm talking to 256 people. That's my sample size. Now I need S. What's S stand for?
2050.
Yeah, S is 2050. S is the symbol for what?
Standard deviation.
Of the
Sample.
sample standard deviation. Oh. Sample standard deviation. All right. 2050 divided by 16. Siri could answer that. I bet it's 128.125. I don't see 128.125 up there. I give up. Math is hard. Unless it's not 128.125. Okay? 2?
To 2 to 3 was 128.13.
Number 6. 6. Oh, sorry. No. Big circle. Yes, that one. Yes. Not a line through. I control 5 when I should have control shift 7. I can't control Z with a pen though. 6 down, 40 some to go. Number 7. Suppose a research firm or research firm, depending on where you're from, conducted a survey to determine the mean amount steady smokers spend on cigarettes during a week. A sample of 100 steady smokers revealed that the sample mean is $20 and the sample standard deviation is 5. What is the probability that a sample of 100 steady smokers is spent between $19 and $21? All right, looks like there's 4 pieces of information that we can identify. And the question is, what's the probability that X is between 19 and 21? I'm going to run out of ink here. All right, 4 pieces of information. What do we got? Very clear.
X bar is 20.
X bar is 20 because it says, if I can find my highlighter, sample mean is $20. So X bar is 20. What else we got? Rachel.
S is 5.
Sample standard deviation, otherwise known as S, is 5. What else we got? Colin.
That is 100.
N is 100 because there were 100 steady smokers. One more. We've got a mean, which we expect. Oh, no, we don't. We only have those 3 pieces because we don't know what mu is. Mu is unknown. Right? Right. But that doesn't mean we can't do exactly what we need to do here. Similar sort of problem that we've seen. Blow it up to the large scale. X bar is 20. S is 5. N is 100. Oh no, I drew a normal distribution that I can't control Z. I sure hope there's a reason I'm allowed to draw a normal distribution. No part of our question said that steady smokers spending is normally distributed, but what do I love? 3 letters. That's limit here. So what?
Never mind.
What are you gonna say?
I was going to say big sample size.
I love a big sample size. Do you love a big sample size?
Big sample.
With a big sample size, I'm allowed to draw a normal distribution because the big sample size says, here's my central limit theorem. With the big sample size, it doesn't matter what shape my population is. The big sample size means I can draw a normal distribution. We thank the central limit theorem for that. But what we have now here is a sample mean that's 20. In fact, that's our sample mean. And what we don't know is what mu is. But we can use how reality normally works. All of these things have one thing in common, and that's that they are observed. So we start with our observation because our goal is to make an inference about the population. Now, it's not necessarily true that these 100 people that we've examined are exactly the same as the 100 people or the however many people in the world who are steady smokers, but we're going to try to make a generalization about the population given this sample. We're going to take a raw score, which is 20, and we're going to convert it to a z, or not a raw score. This is actually the question we're trying to answer. Is we're going to make an inference about the mean. We're going to try to figure out what the probability is that the true mean amount steady smokers spend is between 19 and 21. That's roughly the question that we're going to be answering. But I now have a raw score of 19, 21 to put on my distribution. But I need to be able to convert a raw score of 19 to a standard score. What are they?
Oh, I was going to sample error over standard score, right? No, standard score. Nope, never mind.
Sampling.
Sampling error over standard score.
Standard
error.
Standard error.
There we go.
From the top. Sampling error
Over
versus
standard error.
standard error. So my z-score, sampling error over standard error. Oh no, I guess I should probably calculate my standard error. What's the formula to calculate standard error? There's nothing I can get you, Rachel, yeah.
It's S divided by S over N squared, or N.
Square root. Actually, that's over square root. Yeah?
Sure. Squared.
You got a value for 5 over square root of 100?
0.5.
0.5. Sampling error, 19 minus 20. -1 over 0.5, we get reciprocal. The reciprocal of a half is 2. -1 over 0.5 is -2. Or if I do 21 minus 20, it becomes +2. So now I have a z-score of -2 and a z-score of +2. That bit now allows me to go to my z-score table. And a z-score of 2 gets me an area of 0.4772. And 0.4772. And if I add those two things together, what do you get? Something around, or approximately, or exactly,
Like 95.44.
like 95.44, around 95%. We've actually set ourselves up here by saying, for this sample size, 100, 21 is 2 standard error units above the mean. For this sample size, 19 is 2 standard error units below the mean. We're back to the empirical rule. Approximately 95% of the time, we expect, or about 95% confidence, or about, whatever the case, we're making an answer to this question that says, the probability that the sample of 100 steady smokers spends between 19 and 21, about 95%. 7 is E. 7 down. 4 more to go before we hit the true-false section. Number 8. The Office of Student Services at a large Western state university maintains information on the study habits of its full-time students. Their studies indicate that the mean amount of time undergraduate students spend per week studying is 20 hours. The hours studied follows the normal distribution with a standard deviation of 6 hours. Suppose we select a random sample of 144 students. What's the standard error of the mean? Okay. How do you calculate standard error of the mean? A couple people know. Can't leave without knowing. How do you calculate standard error of the mean? Con, you know? Yeah? Julie, you know?
No.
Okay. Nope. Standard deviation
Understand.
over square root of sample size.
Yeah.
Stay with me.
Standard deviation over a square root.
Yep. That's the standard error of the mean. Whether it's sigma sub x bar or s sub x bar. In this case, we have a standard deviation of 6 hours, and it comes from the population. We have a sample size of, how big is our sample size?
144.
It is. How do you know?
Does it tell us?
Yep. Says we have a random sample of 144. And in order to calculate that, Sounds good to me. Looks like 6/12 or B. How we doing? All right. Give me a check on the pace. Just right, too slow, too fast. Where are we? I see a thumb. Doing good? Doing good? All right. We'll stick with this pace. The Office of Full-Time Students at a large Western State University. I'm not going to say all that stuff again because I have a feeling it's the same question, but different. It's all the same bits of information, but now we're answering a question. What is the probability that the mean of this sample is less than 12.95 hours? So we're going to do same stuff we were just doing. We can extract some of this essential information. We know that the mean, and I'm going to save us just a little trouble because we just read this. We know the mean is 20. The standard deviation was 6. We took a sample of 144. We got a standard error of 0.5. And our question is, what's the probability that we get a sample mean less than 19.25? Remember that one. What is the probability? So when I write that, it's that piece, that the mean of this sample, and the mean is less than, oh shucks, less than, not less than or equal to, less than 19.25. The population is normal, but I couldn't care less because I've got a big sample size. Raw, Z, area, proportion, probability, or percent. As long as the first thing we do is calculate the standard error. And what's our standard error here again, John? 0.5. So we're just running the same thing we did before. We're actually doing it. Our expected mean, mu, is 20. I believe they told us it was 20. Is that right? Is that 20? Mu 20? Yeah. We got a raw score of 19.25, which we're going to convert to a z-score using the z-score formula. You got it?
You redeem it. So sampling error over standard error.
Sounds good. Sampling error over standard error. Sampling error over standard error. Sampling error is always the easy one to calculate because all you do is you take your raw score and you do a little subtraction. And we divide by your standard error, which you already calculated. So you got 0.75 over 0.5. What's up, Mary Claire?
Oh, I was going to say the answer.
Did I do something wrong?
Oh, wait, no, 660.
Not there yet.
Negative.
It is negative. Thank you. Yeah, our z-score is negative. What is that? The 1.5? 1.25? What is it? 1.5? Somewhere over here at 19.25 gets us a z-score of negative 1.50. Oh, you were telling me the full answer there, weren't you?
Yeah, I skipped a step.
I can't skip steps. I'm sorry.
No, that was my bad.
No, it's not your bad. It was your good. 0.4332 is the area that goes here. And why did you go to 0.0668 rather than stop at 0.4332, Mary Claire? You're right.
You take it from 0.5.
Why is that? Why is the area in orange the thing that we want for our answer rather than just this 0.4332? Very good. Because it says less than. Our question, not shown, says what's the probability that x bar is less than 19.25? So we got to go that way. This is the area associated with the z-score. When we get to the final part of the question, it's the probability that x bar is less than, and on that side. Which means the answer to, what question number is this? 9. Thank you. 9 is, say 9 is D, right? Yeah, cool. 9 down, 40 to go. Number 10. The IQ of adults is normally distributed around a mean of 100 or a standard deviation of 15. That's its definition, by the way. If anybody ever, I mean, I'm not a big fan of IQ. Like, as a statistician, as a social scientist, as a person who studied learning, that's a metric that somebody invented a long time ago, that somebody thought of that and somebody believed it. It's kind of like the rainbow connection. That's not the secret knock. That's the new secret knock. Anyway, I'm not a huge fan of IQ. That's not the way learning works. Anyway, they tell you that's the case. They say it's normally distributed around a mean of 100 with a standard deviation of 15. We want to ask the question, what's the probability we could select a sample of 50 adults and find the sample mean to be less than 95? 4 pieces of information that we can knock out right away. What are the 4 given pieces of information? We could also say normally distributed. Katie? All right, well, you got 4 more.
U is 100.
Go on.
Sigma is 15.
Go on.
N is 50.
Go on.
X bar is 95.
Stop there. Because winner, winner, ready for dinner. Yeah, this is the same stuff that we're going to work with. We're going to combine those 2 things to get a standard error. We're going to take this raw score, convert it to a z-score by taking and then we're going to take that to the table in order to get ourselves an area, turn that area into a proportion, which should be greater than or less than 95. Katie?
Less than.
There you go. You could probably accomplish it in a space that size, but I like to write big because I do. Don't judge. Here we go. Mu is 100. Sigma is 15. N was 50. X bar is 95. We want to find the probability that the sample mean is less than 95. IQ is normal, but I got a big sample size, so it doesn't matter much to me. We're going to have a raw score on here of 95. That raw score we're going to turn into a z-score. What's the formula to calculate a standard score? All right, Gerard, it's been like 3 hours. Do you remember, Rob, how to calculate a standard score? Something over something. Something over something. That's standard error. You know what? I'll take that. Standard error. How do you calculate standard score, Gerard? Say it again.
It's sigma over square root of n.
Very good. So we're going to combine those 2 to get standard error. Sigma over square root of n. Right on. Thank you. You got it. So we're going to take 15 divided by the square root of 50. Looks like 2 and something. 2.12. Now we have a standard error. Standard error is part of what I need to calculate a z-score. A standard score is, I don't know. How do we do? How do we do, Julia?
Sampling over standard.
Yeah, sampling error over standard error. I mean, I want to write out the whole thing over and over and over again. That's how I do. Sampling error is always easy to calculate because it's just the difference between something and something else. Sampling error is the difference between what two things? Blank minus blank.
X bar minus mu.
X bar minus mu, that's specific to the mean, but more generically, sampling error is always observation minus expectation. We want to observe 95. We expect 100. The value for the sampling error is 95 minus 100 divided by 2.12. That right there is going to get us a, a remarkably low z-score. Negative 2 points.
36.
Thank you. Confirmation?
Yeah.
Thank you. Now we got a z-score. I'm using the wrong colors. I apologize. I brought all these markers and I can't even use the right colors. Now we have a z-score of negative 2.36, which we take to a table to get an area. 2.0, 1, 2, 3, 4, 5, 6. But the question says probability less than 95. All that's less than 95. 0.0091 feels about right. Is that an option?
Yeah.
Which one?
D.
Yeah, let's use it. 10 is D. It's a big picture. That's where we are. That's our do. Calculate the standard error first so you can put it into this standard score formula. Calculate the standard score, come here. It may seem like this is and I'll call it large, but the magnitude of the z-score, negative 2.36, is large. It's not quite 3, so it's not so much we'd say an outlier, but it may be big enough for us to think maybe we should double check these results. You get a z-score like we did for that California apartment problem, a z-score of 7 or negative 7. You're like, wow, that's crazy. So let's think about it a little bit, and does it make sense? What we're saying here is that a single person who has an IQ of 95 is just a little bit below the mean. One person at 95 would have a z-score of 5 over 15, negative 0.33. Negative 0.33 means the area of 0.1293. Someone at that level is in the 37th percentile. One person, not 50, but one person with an IQ of 95 is in the 37th percentile. They are more intelligent than 37% of people. But if you take a sample of 50 people, what's the problem? What's the probability that you select 50 people at random and their average IQ is less than 95? If you select 50 people at random, you would expect that some of them would be quote unquote smart and some of them would be quote unquote not smart. I use those intentionally. I don't like IQ so much that I still put quotes around it. But dare I not use words like, I don't know, bad words for intelligence. Anyway, you select 50 people at random. What's the probability that those 50 people have an average IQ 95 or below? You're not going to find 50 people whose IQ is averaging 95 or below. It's a pretty rare occurrence. How rare? Less than 1% of the time. When you select 50 people and find their IQ is on average less. Because you're probably going to find some smarter people in there, quote unquote smarter people. Or the answer number 10 is D. Number 11. Bones Bros and Associates prepare individual tax returns. Over prior years, BB has maintained careful records regarding the time to prepare a return. The mean time to prepare a return is 90 minutes. and the standard deviation is 14 minutes. Suppose 100 returns from this year are selected and analyzed, and so on. What assumptions do you need to make about the population to form inferences about the mean? What assumptions do you need to make about the population to draw inferences about the mean? Julia? Nope. I know, and I appreciate it. But we don't have to make that assumption about the population. Why don't we need to make that assumption about the population? I am. When you have a large enough sample size, central limit theorem takes over. When you have a large sample size, the sampling distribution of the sample means is normal. The blue dots that we looked at last Friday. So then we can use these z-tables. Why do we want a bigger sample size? In some sense, question 2 or 3, talking about the accuracy of the estimates. But I happen to like the fact that a big sample size gives us normality in our sampling distribution. So number 11, shape of the population does not matter. Why? Because 100 returns is greater than 30. With the big enough, bigger than 30, with big enough sample size, the shape of the population does not matter. We can draw inferences about the population regardless. Very clear?
Can we go back to number 5 for a second? I just want to what might be a dumb question.
No dumb questions. Come on now. If I could find it. It's.
The one about the rent.
Oh, okay. Yeah. California. Go
Did
on.
you say that one was 1?
It was.
Slot, but if the.
Was it greater than or less than?
It said at least.
Yeah, so greater than, yeah.
So that's asking what the probability of it being more than 1,950 a month?
That's correct.
Oh, okay, never mind.
Okay. No worries. Yeah, because we're talking about at least. 2,000 is at least 1950, so it's going to be on this side. Yeah. All right, first 11 down, we've done some math. Now we've got about 12 true-false questions to go until we pick up with some more concept questions. We're doing well. Sampling a population is often necessary because the cost of studying all of the items in the population is prohibitive. True or false? 1, 2, 3. One, two, three.
True.
True. Yeah. We often take samples because we can't observe the entire population. Remember, you're smarter than you think you are, each and every one of you. You know the answers to these questions. You do. Sampling a population is often necessary because the cost of studying everything is prohibitive. Yeah, it's hard to study everybody. That's why we only do a census once every 10 years. That's why we do presidential elections once every 4 years. It's hard. It costs a lot of money. When doing research, knowing the population mean and other population parameters is essential. How often do we know the population stuff, Cassian?
No, it's not.
Not all the time. Is it essential?
No.
No. Rarely if ever do we actually have population parameters. Sure, we will oftentimes talk about these things as expected values. But that's not saying that we have to know that stuff. 13, 1, 3, false. 14. If the size of a sample equals the size of the population, little n equals big N, we would not expect any error in our estimate of the population parameter. So if our size of the observations was the same as the size of the population, true or false? There's no error between our estimate and our observation. True. Yeah, if you observe the entire population, your observation is the same as reality. I made a mess up here. I can't find the next question. Oh, shucks. And it also shuffles the order. So that one right there was 14. Was true. Yeah, 14 is true, but notice that true is B, not A. Cool? Cool. 15, 1-5. We can expect some difference between sample statistics and population parameters. And the difference between the sample statistics and the population parameter is a thing called sampling error.
True.
True, right on it is. That's x bar minus mu, or observed minus expected. 15A true, 15 down. We're making moves. 16, a sampling distribution of the means is a probability distribution consisting of all possible sample means of a given sample size selected from a population. Woo! Does anybody know what the definition of the sampling distribution of means is? I'll give you a hint. It's a probability distribution consisting of all possible sample means of a given sample size selected from a population. When we did those exercises, or when we did those simulations on Friday, it said, here's a population. Let me take a sample of 10,000 or 100,000 or 1 million or 1.6 million. And we generated a sampling distribution. It was a distribution based on sampling, based on taking a sample of a certain size, 2, 5, 25. But taking that sample of a given size, 2, 5, 25, over and over and over again. Now, granted, maybe it wasn't all possibles, but 1.6 million is a lot of possible samples from a population. And I could have spammed those buttons over and over and over again. But that's what a sampling distribution is. It tells you what are the possible means that you could get from this particular sample. Possible is in possibility, is in probability, is in likelihood. And if you generate a simulation of, let me do this thing over and over, take a sample of 5, plot the mean, take a sample of 5 and plot the mean, do that over and over and over again, you generate a sampling distribution of sample means. 16A. True. That's the thing we were generating. It's the sampling distribution of the sample. 17. If the sampling distribution of the sample means approximates a normal distribution, then the population is normally distributed. True or false? Very clear? That's the right answer. I'm curious to see what your justification is.
It is right?
It is.
Because when they were doing the dispersion thing, you had uneven distribution, but they still sampled into the normal distribution. We said it again.
Yeah, say it again louder. Yeah.
When we did the little blue dots like following thing, it had like different like population means that were not normally distributed, but the sample means always fell into the normal distribution.
Yeah, it didn't. Yeah, the population didn't matter what shape I had up there. Whenever we did all those blue dots and generated sampling distributions, they ended up normal. And that's what this says. It's saying starting with a bunch of blue dots that were normal. Yeah, get in there. Magnetic projector. I don't know why it's not on here anymore. this guy. So it doesn't matter. This can be whatever. But if I take a sample that's large enough, I'm going to take a sample of 25 things from there. I plot a blue dot, that's the mean of those things. Boom. Come on. I'm going to generate a sampling distribution of sample means for a sample size 25. And it doesn't matter what the shape of the population is. This will be normal, no matter what that is. That's Mary Claire's explanation. Right on. Right on. False. 17A, false. Interesting moment. That was awesome. That's awesome. Central limit theorem. I've been teaching central limit theorem for 10 years. And it takes some next level thinking to comprehend all those different pieces. We got so many different words and things. This is tough, but I love it when people get it. Thanks. And they've made my day. May have, I don't know, we'll see. Day's not over. I might get a bacon cheeseburger, and it could be good. But central limit there versus bacon cheeseburger, it's tough competition. 18. The mean of all possible sample means is equal to population mean. The mean of all means is the mean. Makes sense, right? What do you think? True or false? 1, 2, 3. I'm gonna go with true. I'm gonna go with true. And I'm not trying to fool you on that one. But here, we did 700,000 repetitions of taking sample means. These are roughly all the sample means that we could take. This is all the sample means we could take. We could do this again for like a million times. But the mean of these blue dots is about 16, 15.93. That's the skyline up there, and the mean of it is 15.93. The mean of all these blue dots, all these sample means, is the mean of the population. The mean of all the means is the mean. 18 is A. 19. In the sampling distribution of the sample means, blue dots. The standard error of the mean will vary according to the size of the sample. By the way, the standard error, how do you calculate standard error? Yeah. Standard deviation, 9, divided by the square root of the sample size, 25. What's the square root of 25? What's 9 divided by 5? What's 10 divided by 5? A little less than that, 1.8. Sigma divided by square root of sample size gets you the standard deviation of this thing. The standard deviation of this thing is the standard error. Strictly speaking, the standard error is the standard deviation of the sampling distribution of the sample means. It's a lot of different words of the same type to put together, but that's what the standard error is. And our question asks, without skipping back, in the sampling distribution of the sample means, the standard error of the mean will vary according to the size of the sample. So if this number, the size of the sample that we use to generate this, was smaller or larger, the dispersion of these blue dots would change. In fact, why not demonstrate that? That looks like, with a smaller sample size, used to develop this sampling distribution of sample means, we have a larger dispersion, otherwise known as a larger standard error. As the sample size n gets larger, variability of the sampling distribution gets larger. True or false?
True. False. False.
Doing some facial voguing up here. What do you say? Locking it in? Final answer?
False.
False is correct. As this number gets bigger, this thing gets more narrow. As this thing gets more narrow, its standard deviation gets smaller. This thing's standard deviation is the standard error. So, bigger sample size, more narrow sampling distribution, smaller standard error, more precise estimates. Thank you, central limit there. 19, B, false. Or 19 is false, sorry. 20, this is B, this, B, this is conjugation. Conjugation is how you turn B to is. Anyway, about B is turned into honey. The central limit states that if the sample size n is sufficiently large, the sampling distribution of the sample means will be approximately normal, even when the population is skewed or uniform. That's right. Exactly what it said. Kind of looks like magic, too. 20 down, 29 to go. 21. For the sampling distribution of sample means, sampling error will decrease as the sample size increases. This is 21. So here's one of those things that it's not a direct consequence. We know standard error will go down. We know that standard error will get smaller if n gets bigger. We know that. However, one of the reasons a bigger sample size is better than a smaller sample size is, as we saw earlier, your estimates get more precise and you do reduce sampling error. It does happen. You get better. And we saw that if you sample the entire population, if your sample size is the same as the population size, what is your sampling error? What's the value? If little n equals big N, x bar minus mu equals 0. Yeah. Sorry, if your sample size equals your population size, your sample mean minus your population mean is 0. The difference between what you observe and what you expect is nothing, because you observe what you expect. 21A, true. 22. The standard error, am I in the right numbers here?
Yeah.
Yeah. I just need a moment because son of a gun. Anybody want bonus points? All right, someone's got to email me and tell me to change the answer to 22 to B. Because what's the answer to 22?
B.
Yeah. Yeah, no, it's totally, those two things are different. You guys got that, right? Standard error and sampling error, totally different things. Right? All right, better be. If they were the same thing, then z-scores would all be 1. That's the next level joke. 22B. 23. The standard error of the mean measures the dispersion of the sampling distribution of the sample mean. Ooh. So, blue dots, black dots, and all other dots. The standard error is the dispersion, is a measure of the dispersion of the sampling distribution of the sample means. Who's got it? Who knows they got it? Who knows they got this down? Colin, you think you know it? Jack, you think you know it? You don't know it? Standard error. This value, the standard deviation of this distribution, is the standard error. This value, standard deviation, is the standard error. This distribution and this distribution have means, have standard deviations. Were both generated using different sample sizes. If I told you the population standard deviation sigma was 9 and that the sample size was 25, you could take 9 and divide it by the square root of 25. And hey, Julia, what do you get when you take 9 divided by 20? What's 9 divided by 5?
1.8.
The standard error, sigma over square root of sample size, is the standard deviation of the sampling distribution of the sample means. Let's see if I can do this one more time. Get all my movements right. The standard deviation of the sampling the standard deviation of the sampling distribution of sample means given a particular sample size is the standard error. All those things work together. This distribution is different from this distribution because this distribution was formed by taking samples of size 25. This distribution was formed taking samples of size 5. This distribution is wider because the sample size was smaller. This distribution is wider means it has a larger standard deviation. Larger standard deviation means more dispersion. The dispersion of the distribution of means, the distribution which was arrived at by sampling, the sampling distribution of means. You know what? I don't have to mind sampling. I animate it. I'm going to take a sample, and once I take the sample at 25, I'm going to plot a blue dot somewhere on here, probably right here. And then I'm going to take a sample of 5, and the blue dot is probably going to get plotted right here, probably, because this represents what's happened in the past. In the past 600,001 times, we took a sample of size 25. This is what happened. And most of the time, this happened. Most of the time, that happened. All right, that's the last. I'm going to do that for like the next 2 minutes. 23 is true. Standard error is the standard deviation of the sampling distribution of the sample means. 23 down, 26 to go. It's great. Once we get through the next 6 questions, we got 5 math problems to do. But those 5 math problems are going to start developing the habits that we'll see, which is Jeff asks for all the pieces along the way because I want to know that you know process, not that you can get the right answer, but can you do it? And in the event that you calculate something wrong, I still want to know that you can walk through all the steps. So the last 5 math questions are going to ask for all the pieces of the problem along the way, and those will go pretty quickly. 24. The difference between sample mean and population mean is called Mary Claire. Yeah, it's not called Mary Claire. It's called sampling error. 24 is B. 25. All possible samples of size n are selected from population, and the mean of each sample is determined. What is the mean of all the sample means? Should be. Should be. Yeah, population mean. Should be A, population mean. 25 down. Whoa, we're halfway there. 26. Why don't we usually know the true sampling error? In order for us to know the true sampling error, what else would we have to know? not just the sample mean, but
You have to do
yeah. You all right?
Fabulous.
I know. Asked if you were all right.
Thank you.
All right, cool.
You-
Because mu is unknown. Yeah. So in the case of calculating sampling error, how do you calculate sampling error? Something minus something, right? How you do it? Julia?
Epsilon minus.
Yeah. You can always find a sample mean. You take a sample, even if it's only yourself. In the biz, we call that n of 1. You don't want to generalize from n of 1 because n of 1 is just you. And you don't know how unique you are compared to the population. You are who you are. But you can always come up with a sample mean. But rarely, if ever, do we actually know the population mean. And if mu is unknown, 26D, it's hard for us to find the true sampling error, the true difference between what we observe and what is real. Now, we usually talk about what is observed and what is expected, but this can also be estimated value minus actual value. And if you don't know the actual value, you can't find the true sampling error. 26D. Well reasoned. Thanks for sticking it out. I can keep pushing you, or I can cut you slack for the rest of the day after that effort. What do you want?
Keep pushing me.
Thank you. I wasn't actually going to honor your request. Cool, 27. I hope all those answers were right. Felt right anyway. 27. My gosh, how many times do we have to find the mean of all sample means? On the count of 3. 1, 2, 3. Do this one more time, but like deep, like guttural, like from your diaphragm. 1, 2, 3. I just made you all sound like cows. Right? Come on. That's good. I'll go back to beat jokes. Watch me. 28. As the size of the sample increases, what happens to the shape of the sample means? Big sample gives us a shape. What shape does the big sample give us? Normal distribution. I hope that's on here. D. 28D. 29. So here's where we have some little fun. According to the central limit theorem, and this is kind of the nonsense because you're likely going to see a couple things. Increasing sample size decreases the dispersion of the sampling distribution. Yeah, that's true. The sampling distribution of the sample means will be skewed. That's not true. Population mean and the mean of all sample means are equal. Well, I mean, that's true, but that's not necessarily according to the central limit theorem. The distribution of the sample means is approximately normally distributed. We got 3 true statements here. But the real value of the central limit theorem is delta, D. If the sampling distribution of the sample means, those blue dots is normal. That's why we care about the central limit theorem. Not that it gives us better estimates, better estimates as a function of narrow distribution. Not that we know the mean of all means is the mean. Central limit theorem doesn't do that. Central limit theorem gives us normality in our sampling distribution. 29. You got us this far. I can get you the rest of the way. 29 is D. But if you check this out, and we see, I don't know why it says 40 over here. This has got, because it says you select a sample of 40. That's why I got confused. This is question 30, but my paper makes it look like it's question 40 when it's just the end of the sentence. I got an ordinal value confused with a ratio value. It happens all the time. A normal population has a mean of 75, mu equals 75, and a standard deviation of 5. Sigma is 5. You select a sample of 40. You're going to compute the probability that sample mean is less than 74. So for 30, we're doing probability of X bar less than 74. For 31, we're gonna find the probability that X bar is between 74 and 76. For 32, we're going to talk about the probability that X bar is greater than 77. And for the next one, the probability that X bar is between 77 and 76. But all four of those are going to come from the same spot. Pick one. 30, 31, 32, or 33. Pick one.
32.
Thank you. That's correct. The reason I said pick one is because if you go to Module 6, I get to show off some cell shops. Today, which looks like this. Now we're going to walk through one, but our population mean, we said, for this particular problem was 75. Mu was 75. Sigma was what? What was sigma for this one?
5.
5. Thank you. Sigma was 5 and n was 40. Is that right?
Yes.
Cool. That's what we have. Do we know the shape of the population? Is that given to us here?
Normal.
It does say normal?
Yeah.
All right. So we're going to work through one of those. We're going to work through number 32. But there's a tool that's available for you if you want to work through these things or you don't feel like working through all these things. Because I know it's a contact sport. You need to be able to do as many of these as you possibly can. But it's 6 o'clock, and I don't want to be here until 8 o'clock. Do you want to be here till 8 o'clock? I mean, we can hang out if you want. I'm not trying to, though. Like, I mean, we hang out, but I'm not trying to be here doing this until 8 o'clock. The population mean we know is 75. Population standard deviation we know is 5. Population is known to be normal. My sample mean for question number 32 was 77. And my sample size is 40. So if you input those 5 pieces of information which are in blue into this, not only can you see what that would look like if you were to draw the picture with 75 in the middle, you would also see what that looks like if you have a line here on the standard normal distribution, the z-score at 2.5. So sort of sounds like 77 minus 75 is 2. 5 divided by square root of 40. Oh no, that's broken. I mean, we're good. It's approximately 0.8 or 0.79, which rounds to 0.8. Which means my z-score is around 2.5. And then I've got other things on here which will check your work for you. So if you're working on practice problems or you want to generate some examples for you to work on, you can input those things into Blue, and this Excel workbook will show you what the answers to the questions are. So you can get through them with some efficiency. I would expect that the answer to number 32 should be somewhere around 0.0057, because greater than 77 is what we're after in number 32. You guys on board? This is a little tool you can use. If you want to unpack it, you can spend a little bit more time, but it shows you both what you have your inputs here. Greater than 77 would be 0.057, 0057, and that's what your picture should look like. For us, we have a normal distribution with a mean of 75, an observed value of 77, and we want to know the probability that x is greater than 77. So we're working from a raw score, 77, to a z-score, to an area, to a proportion, probability, or percent. In order to calculate a z-score, it's one more time. Something over something.
Sampling error over standard error.
Thank you, Jack. Sampling error over standard error. Or our observed value, 77 minus 75 over, oh shucks, we didn't calculate standard error. How do you calculate standard error? 5 over square root of?
40.
Yep. Which we saw to be something around 0.79 using this calculator. It says standard error for x bar 0.8. We could use that one too. Two over 0.8 is the same as 2 over 4/5, which is the same as 10 over 4, which is the same as 2 and 2/4, which is the same as 2.5. Thank you, fractions. Z-score of 2.5. Gives me an area of about 0.4938, which leaves me 0.0062 over there. Oh no, 0.0057 and 0062 are not the same. However, given our choices of 50%, 99%, almost 50%, or less than 1%, B is the one which makes sense. Good work today. Thank you. Thank you for coming by. So we got 5 practice problems here, but each of these 5 problems are just 5 different scenarios that we're going to do different z-scores for. Z-scores we still take to the area, to the table to get the area. We still use that area to get a probability. But having a calculator that can say, what's the z-score? Well, that's easy. Well, in fact, in all of these problems, we're still using approximately the same standard error in all of them, which is in all of these problems, we're using the same standard error, which is approximately 0.8. So if we're talking less than 74, we need a z of 74 minus 75 over 0.8, which gets us approximately negative 1.2, I think. If we do this one, 74 has a z-score of negative 1.2. 76 is equidistant on the other side. We're just chopping up this distribution in a number of different ways. We go to our table and find the z of 1.2. 0.3849. And what's left over here is something around 11%. And while I don't see this number exactly on our lists, I see something close to it. So I would expect that the answer to number 30 is A. For number 31, I again know that the area is 0.3849. And in fact, that's the same area over here as it is over here. So I'm going to double 0.3849 and get something around, I don't know, 0.78. C. For 32, we executed here. And for 33, between 76 and 77, that's the harder one, because 76 and 77 are both on the same side of the mean, which is 75. So the first thing we do is find everything that's in orange. And everything that's in orange here, we found in the previous problem. And the z-score was 2.5. This area was 0.4943, something like that. I think these types of problems are the most challenging because the picture tells you that you have to subtract this piece from everything in orange. You have to subtract this piece in red from everything in orange to get just what's left right here. But in the previous problem, we saw that the area was almost 0.5. So we can just take away 13% from 50% and get something hopefully around 35 to 36%. Well, we can't because Jeff can't do math without a table. That makes more sense. 76. Gave us a z of 1.2. Z of 1.2 gives us an area of 0.38. So we have 0.3849. About 38% subtracted from 49% gets us something around 10%. I need to take a deep breath after that. I don't know about you. How much of that did we gather? Well, a lot of holes in our buckets. We carrying most of that. It's just different ways to chop up this distribution. We can do them over and over and over again. But I think we can pick one of the four for each of these scenarios. Calculate the standard error. see how we need to draw our picture, and then effectively we're just doing this piece over and over again, which is moving areas around. But the answers, that's what we're after. 30, 33 are those. $34. Means we have 15 questions, 18 minutes. We can do efficiency. According to an IRS study, it takes a mean of 330 minutes for taxpayers to prepare, copy, and electronically file a 1040 tax form. Don't be fooled, doesn't matter which tax form it is. Well, that's a specific one, but don't let the numbers confuse you. By the way, it doesn't take you any time at all if you don't do them. Pro tip. This distribution of times follows the normal distribution, and the standard deviation is 80 minutes. A consumer watchdog agency selects a random sample of 40 taxpayers. Got a few pieces of information here. What are the few pieces of information we have here? Take on. Yep. What else we got? Cassie?
Sigma's 80.
What else we got?
And it's 40.
And it's 40. Right on. Question 34, we want the standard error of the mean. All right. Let's see. Coming all the way back up. We got it before, got to make sure. Automatic, we're smoother than calculation error. That's the standard. The standard. We want the standard error. Say that with the obvious tone. We're getting it automatic. I love it. That's what we need. I said, like Gino says, it's not so you get it right, it's so you can't get it wrong. And I still get it wrong, so it's just an aspirin cold. Square root of 40, I should know by now, it's 2 square root of 10. Square root of 2 is 1.4. Square root of 5 is 2.2. 1.4 plus, or no, it's 2.8, it's 28. Is 3 change, 3 is 6. So 80 over 6 should be about 12 and a half, Caroline?
Yeah.
12.65. Now we want to do greater than 320 minutes. We have a At this point, I care about the standard error at being 12.65, and mu is 330. And my sample size, I don't even care about. This is really the 2 pieces of information I need now. 330 is in the middle. I need something greater than 320. Greater than 320 means I'm going to be adding 0.5 to whatever I find in here. In order to find that, I got to take 320 and convert it to a z-score. Now we come back. Standard score. Something over something. Sampling error over standard error. 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 That seems close. 0.8 something?
0.79.
0.79? Oh, it's just bigger, not smaller. Thanks, John. Negative 0.79. Thanks, John.
No problem.
Here you go. I do appreciate it. That's a genuine thanks. I don't have to do all this math. I'm glad that you're learning. I'm glad that you're doing the math for me. Glad that y'all represented today. Very well. Yourselves were represented very well. Z is negative 0.79. Gets me an area of 0.2852. So the answer to 35 should be something around 78%, 79%, 35 down, 36, sample mean greater than 350. Greater than 350. So we're going to take 0.5 minus whatever area we get here. When I was over here, my sampling error in the previous one was negative 10. What's my sampling error in this one? I was negative 10 before, now what on? Yep. Say again?
20.
20. Compare 20 and 10. 20 is blank as much as 10. Twice as much as 10. Here's a property of raw scores and z-scores. Or rather, sampling error and z-scores. Double the sampling error, double the z-score. The sampling error before was 10, negative 10, 10. The distance was 10. 10 is now 20. 0.8 is now 1.6. Or 1.58. Point 4429 is what we're after. Somewhere around 6% should be my answer to 36. $36 is D. Now for 37, we have to go between 320 and 350. We have to go between 320 I'm going to add that number to that number. I'm going to add 29%, 44%, which otherwise known as adding 30 to 43, which gives me about 73%. $37C. Got 12, 8 minutes to get 12 done. Our rate is going down. I wonder if we can meet the deadline. There's no deadline. Next one. Power through, sprint to the finish. Help me out. In the Department of Education at your university, student records suggest the population of students spend an average of 5.5 hours per week playing organized sports. The population standard deviation is 2.2 hours per week. Based on a sample of 121 students, I like that number. Healthy Lifestyles Incorporated, HLI, good to know, would like to apply the central limit there to make various estimates. Thanks, Rachel. Great job today. Standard error of the mean. How do you calculate standard error? That's tough. That's toughness. Sigma is standard deviation is 2.2. My sample size is 121. Boy, do I like that number because 2.2 over 11. 0.2? What do you say?
Yeah.
I say yeah. 38.2. What's the chance HLI will find a sample mean between 5 and 6 hours? Look at your answer choices. 5 hours? How many standard error units below the mean is 5 hours? A lot or a little? Sampling error, 5 minus 5.5. 0.5. 0.5 over 0.2, that's my z-score. We looked at this before with the empirical rule. We know that 5.5 is in the middle of those two. Now we're just thinking 5.5, 0.2, 0.2. 95% of things should be, or rather 95% of samples with that sample size, 95% of things from a sample size of 121 should be within 5.1 and 5.9. We're talking about between 5, 6. That's a z-score of negative 2.5 and positive 2.5. A lot of stuff should be within 2 standard error units. Even more stuff should be within 2.5 standard error units. Given these 4 options, which one of those represents a high proportion of stuff? Colin? That is correct. Oh, I should have said bravo. Because it's also B. Anyway. No time for jokes. 39B. How strange would it be to obtain a sample mean greater than 6.5 hours? Strange or not strange?
Strange.
Strange, like L.
Should that be B?
You're B. 40B. Unlikely. All right. Calculate the probability the sample mean will be between 5.3 and 5.7. That's 41. But again, we're talking empirical rule at this point. It's not A. 5.5 is the mean. The standard error is 0.2. Between 5.3 and 5.7, how much stuff should fall within one standard unit? Standard deviation, standard error. How much stuff falls within one standard unit of the mean? How much stuff? What proportion? 68. I should hope one of these answers is 68. That's not 68. That's 68. What number was that? 41?
Yeah.
41, 68. Now we got Power Plus, and we got Churchill's Grocery. Hey, we got to do the standard error. We got to talk about the shape. We got to come up with some proportions. Proportions. Solve for proportions. And then this one, we got to get likelihood like a proportion, a likelihood like a proportion, and then another proportion. So we're at about 6:30. Who wants to stick it out? Who wants to stick it out to the end? You want to stick it out to the end? We're here for the long haul. All right. Thank you. I told you this one was a grind. I'm trying to, since we've done a bunch of these, but also like give you a little breathing time. But let's just do it now. 42. Power Plus indicates that batteries used in remote control toy cars. We got mean life of these batteries is normal. Has a mean of 35 and a standard deviation of 5.5. Then we're going to test 25 batteries. Standard error. Gerard, standard error.
Sigma over square root x.
Thank you.
I'm sorry, man.
No apologies, you got it. Told you we're gonna leave you knowing that. 5.5. By the way, 5.5 is the standard deviation. 5.5 over the square root of 25. Well, that's good because that's 5.5 over 5. Which I believe is 1.1. 42C. What can you say about the shape of the sample? Oh, we only took a sample of 25 batteries. And 25 is not greater than 30. So we can't say that the sampling distribution of means is normal because the sample mean is less than 25, right? Help me, carry me.
So it's
Nope. Joe,
It says normal.
what says normal?
Question.
What is normal though?
The probability distribution.
Yes, that's fair. The mean life, the average life of those is normal. All right, circumdistance square. 43, because it says normal. 44. What proportion of samples will have a mean life of more than 36 hours? Z-score, sampling error over standard error, 1 over 1.1, right? Because the mean is 35. 1, which is 36, minus 35, over the standard error, 1.1. 1.0 over 1.1, something like 0.9. 0.90909090909. Should go 1. So we got a z-score that's almost 1. .3186 is our area. Cleveland Browns would say 0.3186. But we're better than that because we know what we need is greater than 36. A, B, C, or D? 1, 2, 3? B. 45. What proportion of the sample will have a mean life greater than 34.5? Greater than 34.5. Eliminate 2. Eliminate 2. B and C. Why? They're less than half. It's going to be either that one or that one. You could calculate it and do the work, or let instinct take over. What do you like? I think that's a pretty good answer. Let's see what we got. The z-score would be 0.5 over 1.1, which looks like 0.4. Five? Is that going to be 0.45?
Yeah.
Yep. Which means the area 0.1736. Add them up. 46. We're so close to the end. What proportion of the sample will have a mean life between 34.5 and 36? What do we got to do with that one and that one? Jill, add them up. 17% is 32%, gives me about 49%, 46B. All we did was say between 34 and 36. We got this from the previous one. We got this from the previous one. 46B. Churchill's grocery store, 47, 48, 49. The mean amount of typical purchaser is 34.23, whatever those numbers are, with another number. Assume the distribution of the amounts follows normal distribution. We got a sample of 50. If I'm losing my words, you must be losing your mind. Is that right? It's okay. You're working and learning. I'm trying to just be. We got a couple pieces of given information. What's the mean according to the problem? Population mean, what the mean amount of customers spend? How much? 2350. And that does not come from a sample. We're just told to believe that. The standard deviation is Abe Lincoln. N is 50 customers. We're going to combine those two. And I got this one, sigma over square root of n. Five over square root 50 gives me about 5 over 7. It should give me something on the order of 0.71. I have a standard error. Now I got to get a sample mean of at least 25. Oh, I could answer this without even doing that. Anybody see the answer already?
50.
Not quite, a bit too much. 71 cents is my standard error. What's my sampling error? John, what's my sampling error?
2350.
That's my mean.
25.
That's my other mean. We take one mean, subtract the other mean, we get a sampling error.
Yeah. Just 150.
Yeah, $1.50. Sampling error is $1.50. Standard error is 71 cents. A pretty big Z, right? 150 over 70. Jill, A is a little too big too. C. I think it's C. We have mu is 2350. Our X bar is 25. Our standard error is 71 cents. A raw score of 25 has to go to a Z as 150 over 71, which gives us a Z score of 2 point, no, something. How much is left up there? So it's a 4, so 8, so 8 over 70. 8 over 70 is about 9. So I want to say 2.1. 2.1 what? 2.11? 2.14? Hey, you know what? Let's call it 2.10 or 1, 4. Somewhere in the 2.1 range. But all of those things in the 2.1 range are about 48%. However you choose to round that Z-score, 2.11 or 2.1 whatever you get there in the Z-score of 2 point, you name it. You're getting an area here of about 48%. Which means that greater than 25 is approximately 2%. Too big, 2%. For 48, we want to be greater than 2250, but less than 25. That is approximately, a little bit more than 1 standard deviation away. But whatever the case, it's going to be an answer that's greater than 48%. Because what we want for number 48, that is between 22 and 50. So it's got to be greater than 48%. One of those looks reasonable. One of those looks unreasonable. Which one looks reasonable? See? See? Could be hot for me. Let's try it out. We want to get a z-score for here. 2250 minus 2350 over 71 cents. Gets us $1 over 71 cents. Which is 1.4. Is that right? 1.39? 1.41? Thank you. Negative 1.41. Oh, you know what? You are right. 1.41. I was wrong. My reason, 0.42, or around 42%. 42% was 48%. Gets how many percent? 9%. Between what limits will 90% of the sample means occur? That means I want 45% here, 45% here. I'm worked back from a proportion, 45%, to get me a picture. A z-score of around 1.65. The upper bound is going to be mu of 2350 plus 1.65 times 71 cents. I don't know what 71% of 1.65 is. Feels like $1.40, $1.30. What's 71% of 1.65? Hey, maybe Siri's around. Hey, Siri? $1.17? Cool. So we're going to take $23.50, add $1.17. You get $24.67. That's the upper bound here. $24.67 as the upper bound. Is that one.
For 22, I think you said you put it in wrong yourself, so should we put in?
Put in the correct answer and I'll update the key.
Okay.
As long as someone reminds me to update the key. I think Mags may have jumped on that, but I don't mind. Y'all did great. We stuck it out here. Hey, 2 hours and 42 minutes for 49 questions. That's an average of some minutes per question that I can't calculate. I don't expect any of you to as well. Like I always think about this is like, I know this stuff. I should be getting this right. I don't have to learn it. The energy for me comes from repetition and trying to drive it into you guys. But you guys are making new wrinkles in those brains. It's good work sticking it out. You earned it today. You definitely earned it today. Proud of you. Keep it up every day.